The Paartalbahn is a 67-kilometer rail line connecting Augsburg Hauptbahnhof to Ingolstadt. On May 7, 2018, a regional passenger train approached the station at Aichach. Waiting on the same track was a stationary freight train carrying timber. The station was controlled by a mechanical signal box dating back to 1949. It lacked automated track vacancy detection, meaning the infrastructure itself could not electronically sense if a section was occupied. The dispatcher mistakenly routed the incoming passenger train onto Gleis 2 without confirming the track was clear. The approach to the station curves to the right, which meant the driver of the passenger train could only see the freight cars once they were 130 meters away. At 90 kilometers per hour, the distance was too short to stop. The collision killed 2 people and injured 13. It demonstrated the risks of relying on human sight and a centralized, aging infrastructure to track train positions. To prevent another Aichach, the standard industry response is to retrofit the tracks with wayside infrastructure, like magnetic balises or axle counters, to detect occupancy. But scaling this hardware across an entire network is a logistical hurdle. Securing the 67 kilometers of the Paartalbahn requires thousands of individual nodes. Every sensor requires excavation and ongoing maintenance, making the capital expenditure for regional lines prohibitive. Physical sensors also limit the network to fixed blocks, safety buffers that dictate how many trains can use the line. Capacity could be much higher with moving blocks, where a dynamic safety zone follows each train continuously. To reach that level of network capacity, modernization requires moving the intelligence off the track and onto the train. Engineer Oliver Heirich's dissertation at the Technical University of Munich provides the theoretical framework for moving localization intelligence onto the vehicle. This requires track-selective localization. Safety depends on knowing exactly which of multiple parallel tracks a train occupies. Satellite navigation systems like GNSS cannot reach this precision. A standard GPS error radius can cover both a primary line and a diverging track at a switch. Multipath errors in urban canyons and outages in tunnels make satellite data unreliable for distinguishing parallel paths. Since satellites cannot differentiate between rails, the train needs an independent onboard data source. The definitive solution lies with the Inertial Measurement Unit, or the IMU. Because rails constrain the train's motion, an IMU records a kinematic signature of the track geometry, measuring yaw rates and lateral acceleration. These signatures correspond to the physical layout. A curve leaves a specific inertial footprint. Heinrich's model uses a Bayesian framework to fuse this accurate motion data with noisy satellite pings. Bayesian estimation updates the train's predicted position by calculating the likelihood that incoming sensor data matches the track's known physical traits. By continuously filtering these imperfect satellite coordinates against precise motion data, the onboard computer definitively determines its exact true location. To find its location using motion signatures, the train must have access to a highly accurate digital track map. On legacy networks, these maps are often outdated or entirely unavailable. This creates a logical loop. The train needs a map to find its position, but needs its position to create the map. The solution is RailSLAM. The algorithm learns the track's geometry while simultaneously calculating the train's location within that emerging data. RailSLAM allows the train to build its own operational model of the environment without relying on external wayside hardware. The most difficult hurdle for onboard localization is the railway switch, where rails diverge in close proximity. As a train crosses a switch, there is a moment of uncertainty where 2 paths are equally probable. The system resolves this using a multiple hypothesis tracker. The tracker maintains 2 possibilities, one for the straight path and one for the diverging path. The IMU data soon provides an answer. If the train diverged, the sensor registers a lateral force. The algorithm immediately removes the incorrect hypothesis. This robust logic guarantees 100% track selectivity in real time, making physical wayside balises completely unnecessary for positioning. Heinrich's model was tested over 230 kilometers using sensor data from a standard regional train in regular service. The data was collected on the Paartalbahn, the same line where the Aichach collision occurred. The Bayesian filters achieved 100% track selectivity. When trains can pinpoint their own locations, they can broadcast that data to each other using a Railway Collision Avoidance System, or RCAS. RCAS allows trains to manage their own safety, identifying obstacles and blind spots that legacy infrastructure might miss. If both trains at Aichach in 2018 had been equipped with RailSLAM sensors, the outcome would have changed. The onboard RCAS computers would have detected the overlapping positions on Gleis 2 long before the trains were in visual range. This direct communication would have triggered emergency braking, neutralizing the dispatcher's error. Mapping tracks on board also enables virtual coupling, where trains share the same rail separated by only a few meters, synchronized by algorithms. By moving intelligence from the iron tracks into onboard algorithms, the railway becomes a proactive, autonomous ecosystem.